Okay, well, this is the math part of the details about mastering system. Our mastering system, there are three kinds of motions, which are undamped motion, underdamped motion, and critically damped motion. For the undamped motion, the system is free and no interference, and it's undamped. There's no friction, there's no air resistance. You can see at the picture on the right side, the string constant is K and the mass is M. And what we should do is we lift the mass on the string system up to where x equals to 0 and velocity equals to 0, x equals to 1 and the velocity equals to 0. So as our example, we have the x of 0 equals to 1, which means the x-axis is 1 and x prime 0 is 0, which means that the velocity is 0. There are two laws that we use, which is Hooke's law, F equals to minus kx, and k is the string constant, and Newton's second law, F equals to ma and equals to mx double prime. And we combine these two laws together and we get mx double prime equals to minus kx, and we let beta equal to k over m equals to 4. So we get the equation x double prime equals to minus 4x. And we can see that the force of the spring exerts is proportional to how far you pull away, and it always pulls back in the opposite direction. For our undamped motion, this example, we solve the equation, and we get x of t equals to cosine 2t, and x from t equals to minus 2 sine 2t. And we can get an equation with the waveform in this picture, and we can see that if we divide minus 2 from x2, and we can get cosine 2t and sine 2t for x1 and x2 over 2. So we can see that x squared plus x prime over 2 squared equals to 1. And we want to find the trajectory of our simulation, but we have to find a relation between x1 and x2. So we have to make the t parameter disappear. So by our implicit differentiation, we can get that dx2 over dx1 equals to minus 4x1 over x2. And from our x squared plus x prime over 2 squared equals to 1, it is an ellipse on the x1 and x2 phase plane. And we can see that when t equals to 0, x1 equals to 1 and x2 equals to 0. So it is the spot which is the tangent is infinity. And when t equals to pi over 4, x1 equals to 0 and x2 equals to minus 2, and the tangent is 0, which is the bottom of the ellipse. And if we change the first initial position of x of 0 to a, and we get the equation of the general case, which is x1 over a squared plus x2 over 2a squared equals to 1. And we can have different trajectory of x1 and x2 on the phase plane. And for our underdamped motion, the system is no interference, resistance, and the resistance that causes the damp is by friction or the medium. And we plus alpha, the damping constant, into the equation of undamped motion, and we get mx double prime equals to minus alpha x prime minus kx. And if we move the left hand side of the equation to the right hand side of the equation to left hand side, and divided the third thing by m, and we can get bx double prime plus bx prime plus ex equals to 0, and x over 0 equals to 1, and x prime 0 equals to 0. And b equals to alpha over m, and c equals to k over m. And there are three types of solutions for when d is equal to b squared minus 4c. And if d is smaller than 0, it's underdamped. And as our example, we get we let b equal to 2 and c equal to 5, and we solve the equation, and we get x of t equals to e to the minus t cosine 2t plus 1 over 2 e to the minus t sine 2t, and x prime t equals to minus 5 over 2 e to the minus 2 e to the minus t sine 2t. And this is our waveform, and we can see at the x-axis that is obviously that there are many points on the x-axis on the line on the waveform, and it means that it's gonna stop for some point in human's view because it is so small and take away the distance to travel. So it is still oscillating forever above the x-axis. And from this equation, we can see that when t comes to infinity, x prime goes to 0 and x goes to 0. And this is the simulation of x1, x2 phase plane. To get all the trajectories, we make the x of 0 equals to a, and we can get different kinds of simulation trajectories. And this is general solution of underdamped motion. For critically damped motion, we can see that d equals to b squared minus 4c equals to 0. And as our example, we let x double prime plus 4x prime plus 4x equals to 0, and we can get a solution. X of t equals to e to the minus 2t plus 2t e to the minus 2t, and x prime t equals to minus 4t e to the minus 2t. This is our waveform, and you can see it's obviously that when t goes to infinity, x and x prime both go to 0, but it never goes to 0, but very close to 0. And this is a phase plane that we simulate for the critically damped motion, and for the same method, we make the implicit differentiation, and dx2 over dx1 equals to minus 4 minus 4x1 over x2. And it's obviously that when it starts at a0 and it goes to 0, 0, 0 very quickly. And the right hand side of the phase plane is when a is larger than 0, and the left hand side is when a is smaller than 0. And this is a reference. I'm making it in a math lab. And thank you for listening.